In this lesson we're going to continue to look at the heat loss problem. In the last lesson we looked at ways in which heat can be lost from an object, and in this lesson and the next lesson we're going to look at what affects the rate at which heat can be lost from an object. Okay, so you're probably aware that if you've got a very large mug of tea and a tiny cup of tea at the same temperature, then the temperature of the smaller cup of tea will fall a lot faster than the larger cup of tea. Now there's an experiment which demonstrates that in the practical demo section under heat, so you may like to look at that. So what affects the speed at which heat is lost? Well, first of all, in our 2 cups of tea we know that heat is stored really in the volume of the object. So the bigger the volume, the more heat that can be stored. So while heat is stored in the volume of the object, it will be lost through the surface of the object. So heat is lost through its surface. So qualitatively we can see that the bigger the volume of the object, the more heat can be stored, while the bigger the surface area of the object, the easier it is for heat to be lost. So we can say that the rate at which heat is lost from an object, such as this hot cup of tea, to its cooler surroundings depends upon 2 factors. The volume, that's the amount of heat that it stores, and the surface area through which the heat is lost to its surroundings. So we can say this, that proportionally the heat loss per unit volume of the object in some given time is proportional to the surface area of the object divided by its volume. So this factor here, this ratio of the surface area to the volume of the object, is very important in determining how quickly the temperature of an object will drop. So let's just consider some simple geometrical shape, such as a cube. Now these 3 cubes are all made of exactly the same material, and let's suppose they're all starting at exactly the same temperature. And you can see we've got a small cube with a size 2 centimeters, then another cube 4, and then another 8. So what we want to do is work out the ratio of the surface area to the volume in each case. So our surface area of the small cube is 2 times 2, so each face is 4 centimeters squared, multiplied by 6 is 24 centimeter squared, while its volume is 2 times 2 times 2, which is 8 centimeters, which is 8 centimeter cubed. So this important ratio, S to V ratio in this case, is 3. Okay, and if we go to the next cube, we double the size of the cube, then the surface area becomes 96 centimeters squared. That's 16 multiplied by 6 faces, and the volume will be 4 cubed, which will be 64 cubic centimeters, and the ratio of the surface to volume in this case is going to be 1.5. So we halve that S over V ratio. If we double that again, then we have now, so if we double the size of the cube again, then we now have the surface of each cube, the surface of each face is 8 by 8, which is 64, multiplied by 6, which is 384 centimeters squared, and its volume is 8 by 8 by 8, which is 512 cubic centimeters. That gives us an S over V ratio of 0.75. Okay, so each time we double the size of the cube, we halve this S over V ratio. So we can say that the rate at which heat is lost from these 3 objects decreases as their volume gets bigger. So as a general rule, we can say this S over V ratio, that's the ratio of the surface area to the volume of the object, decreases as the object gets bigger. Now this is very important in the animal kingdom. So we're going to be considering this heat loss problem in the context of mammals, for example, in particular, and the problems that they have with regard to retaining their heat. So what we're saying here is we've got 2 very familiar animals. We've got a great big huge elephant and a tiny little field mouse, and they're clearly not really in the the correct proportions here, although this field mouse would be a little bit scary, I think, if it was that big, but you get the point. Now, both of these mammals basically have to maintain their temperature at about 35 degrees Celsius because they are warm-blooded mammals, right? So roughly around 35 degrees Celsius. Doesn't matter how big they are, they've still got to keep their bodies to that temperature. That's the typical temperature of a warm-blooded mammal. So their problem is, how do they maintain that temperature? Well, we can see that the field mouse has a much bigger heat loss problem than the elephant. Because it's a lot smaller, the ratio of its surface area to its volume is a lot bigger, as we saw in the case of the cubes. Okay, the ratio of the surface area of this small cube to its volume is a lot bigger than the ratio of the surface area to volume of this cube. As a result, the field mouse will lose heat at a greater rate than the elephant. In order to maintain its body at this temperature, both animals have got to eat food. They digest the food. Glucose is transported to their cells where it's burnt in oxygen, and that generates heat, and that helps to keep their body at that temperature. But because the field mouse has this bigger heat loss problem, it has to compensate that heat loss by eating proportionally a lot more food than the elephant. That's to say, the amount of food that a field mouse eats in one day divided by its volume is actually bigger than the amount of food that an elephant eats divided by its volume. So these poor little animals here have to constantly eat in order to keep their body temperatures at this temperature, while larger animals can go about life in a more relaxed way. So it's not just the size of an object which affects the rate at which heat is lost, but it's also the shape of an object. So in the next lesson we're going to have a look at how shape affects the heat loss problem.